Okay, thank you for the introduction, and it's my pleasure to give a talk here. Okay, today I'm going to give a talk about actually it's combined with two papers. The first paper is a joint work with Jamie Mingo. It's about infinitesimal operator, and so will be a first half of my talk. The second half of the talk is about my joint work with Mawabana. About I try to compute the law of the polynomial in monotone independent elements. Okay, and by the way, this paper just appeared this morning, okay, on archive. Okay, so first let's quickly review what's infinitesimal free. Infinitesimal free is when you have a non-commutative probability space, we consider one more state, or maybe sorry, I shouldn't say state. The free point is a linear functional, also from A to C, but we're sending a 1 to 0. Okay, that's a very simple algebraic definition. And later on, there's a notions, some generalized of sorry, some generalized of the freely independent is called infinitesimal free. Okay, so we consider similar, you can see like for the assumption, we have the same assumption, but if for freedomness, we have the first line. The phi of the alternating A1 up to AN will be 0. But for infinitesimal free, we're adding one assumption for the property for the free point is as follows. Okay, let's say infinitesimal free, and then for the infinitesimal free, that's corresponding cumulant. We call infinitesimal free cumulant. Okay, so here you can see it's also the moment cumulant relation. Oh, can you see this one? Yeah. Okay, anyway. Okay, it's also like a moment cumulant formula, but it's for the infinitesimal free version, which means the left-hand side, we consider the phi point instead of phi. And right-hand side, we consider something called a partial kappa pi. So, okay, for the partial kappa pi, what's that? For the partial kappa pi, when you're given a partition pi, there are several blocks. Each time we're choosing one block, we put it on the point. And all the remaining one, we will keep the original one, like this. Okay, that's the way we define using the recurrent relation. We can define what's the, okay, the infinitesimal free cumulant. Okay, so similarly to the freely independent and the relation to the free cumulant, we have a very good way to using cumulant to understanding the infinitesimal free. It's a work by the Enunica and Marcin Favier in 2010. They proved that infinitesimal free is equivalent to a eventual missing free cumulant and the infinitesimal free cumulant. Okay, so now let's move on to some maybe we should the new notion. Okay. So for a given element A, now we give a name we call under infinitesimal non-commutative probability space. For a given element A, we call infinitesimal operator. What's an infinitesimal operator? We consider the behavior is like a delta 0. So it's like a delta 0. So you can see we assume all the moment kill. Okay. But we don't have any other assumption for the phi point. So the phi point can be non-trivial. Okay. This kind of operator we call infinitesimal operator. So you can imagine for a matrix model, it can be understanding as a finite rank matrix. When you consider limiting behavior, it will be killed by the normalized. Okay. Okay. So what's the property of infinitesimal operator? Okay. First, you can easily prove that the all infinitesimal moment is equivalent to the it's equal to the infinitesimal cumulant. Okay, that's the first thing. And second, if you want to understanding, if you have two elements, S1 and S2, and we assume they are infinitesimal free, and we further assume one of them is infinitesimal operator. And how can we study the commutator and anti-commutator? So, so when you consider commutator and anti-commutator, so you can imagine when you consider phi prime, by moment cumulant formula, when you're writing as a cumulant form, but first we have a vanishing or missing cumulant. So we know x1 only can connect it to x1, s2 only can connect into x2. So we separate these two groups. And second, the s2 only can be chosen to be the block which come with a prime, since we assume that x2 is an infinitesimal operator. Okay, so based on this observation, then we can compute in precisely what's the phi point of the PM and the phi point of QM, which is we know the precise formula for the commutator and anti-commutator for the infinitesimal law. Okay, another thing is needs to be mentioned that okay, in the work by Colin Hasabi-Sakuma. Oh, sorry, go ahead. Sorry, you say the IID Gaussian? Yeah, not self-adjoint, just IID Gaussian. Mm-hmm. Right. Then all the moments will manage. All yeah. Thank you. I didn't think about this one. Yeah. Okay. So for the Colin Hasabi-Sakuma work, they consider something called cyclic monotone, and there's a very good connection between cyclic monotone and the infinitesimal free. So they prove the result for the commutator and anti-commutator in cyclic monotone case. And further on, in 2019, in Ottavio and the agent's work, they proved that, okay, they found another way to solve the commutator and anti-commutator in cyclic monotone by using matrix, some matrix property. And we will see that property later. Okay, okay. So now let's briefly introduce in something, Boolean cumulant. So when you give a non-commutative probability space, the Boolean cumulant is actually a sequence which is divided inductive terms by this formula. So you can see it's similarly to the free cumulant, but you consider the interval partition instead of the non-crossing partition. Okay. But why we're introducing the Boolean cumulant? Since Boolean cumulant has a very good relation with the infinitesimal free operator. So now let's further introducing another definition. Okay. So when you give an infinitesimal non-commutative probability space, we consider something J. And we give a name, it's called infinitesimal idempotent. Okay. So you can imagine the idempotent means the J squared equals J, and since the infinitesimal operator, so it means all the moment Q. Now if we further assume the phi point of J is non-zero, then we can well define this state, the psi A, by this way. Okay. And it's very easy to see this A comes with this another new state psi. It's another non-commutative probability space. Okay. But why we consider this? Since they have a very beautiful property. So we can see, let me jump one more. Okay. So if you're given a unital subalgebra, if we consider B is infinitesimal free from J, okay, then you consider such space JB, which is sorry, so I should mention this. Okay, J1 is a J per, which means I consider something called J1, which is 1 minus J. J minus 1 is J. So then, now I consider algebra generating by those things. It's J epsilon 1 A1, J epsilon 2 A2, and so on. Okay, each time J epsilon 1 can be choosing J or J per. Okay, if we consider such algebra, then for study those kind of thing, which means if we want to study the size of those kind of element, okay, then this one can be calculated precisely by the Boolean cumulant. Okay, so you can see here, now for the size of all these streams, they have many J and J per. As long as we from J move to another J, then this one will corresponding to the first cumulant, Boolean cumulant. Then we keep going from second J, and then lots of J per move to second J. Then we got the second cumulant, Boolean cumulant. So this one can be calculated precisely by using Boolean cumulant. Okay. Yep. Okay. So sorry, maybe quickly recall. Okay. So JB you can see here is defining by all the possibility of algebra generating by those themes. And each time J epsilon 1, J epsilon J can be choosing J or J per. But if we further consider subalgebra, which means we assume, okay, the JAB, okay, JB is a unit, is a subalgebra of JB, which we require the J epsilon 1, J epsilon 2, and so on. They need to be alternating, okay, which means epsilon 1, epsilon 2, and so on. The alternating one needs come from the needs to be different, okay. Then under this assumption, it's called JAB, okay. Then we have a following theory. Now, if you're given two unital subalgebra of A, B, and C, and we assume they are infinitesimal free from J, okay, then we have this result. The J, capital JB, JC, This one and the C, they will be monotone independent with respect to the side. Right? But if we further assume, now from the assumption, we only assume B and C are infinitesimal free from J. But if you further assume the relation for B and C, if they are free, then we have a further result. The JAB and the C, they will be independent. Oh, sorry, monotone independent. Okay. Yeah, that's an abstract way. And now let's see some link to random matrix. Right. So first, if we fix something a not in M, then we know, okay, we consider some matrix. Then we cutting this matrix by 4 pieces, 4 blocks. Yeah. Then what a partial trace means? So the partial trace for a given matrix or random matrix is divided by this way. Now we fix the a not. So now we only consider the behavior of this one, which means we consider normalized trace, but we only pick up the first block. This block. Okay. Yeah. Then this one we call a partial trace. Okay. In Lenshevsky's result in 2014, he shows that as long as the AN and the BN are Gaussian independent, GUE independent, then we consider the TAM and the BN, they will be asymptotically monotone with respect to the psi m. Okay. And the TAM will be chosen by this way, which means these 2 blocks, we replace 0 by, sorry, question? Yeah. We replace these 2 by 0. Okay. Then we call TAM. Okay. And then later on, I try to show that using our result, we'll recover this one. And actually, we can say more. So, okay. So for a GM, if we consider this matrix, we consider 1 diagonal matrix by first a not matrix, and all other we put 0. Then we can easily to see the TAM, what we saw before. It's nothing but the JN, AN, JN per plus JN per AN, JN. And if we divide in the phi m point JM by, okay, this one we consider the non-normalized trace, then which is a not. And the phi m point of AN, JM, we do the similar way, you can observe. Then we'll got nothing but expectation of a non-normalized trace for the not. First a not matrix of AM11. Then, which means if you consider this one dividing this one, we got back that one. Expectation trace. Then what's this one? If you just back to check, yeah, it's exactly phi m. Okay, but what's this useful? And now we need to, okay. Then let's recall a nice result by Benson Au. He proved that as long as we have the Wegener's matrix, and there are some unit, there are some ENIJ, which means only IJ position 1, all other are 0. And the Kn we consider the O1 matrix. And in Benson's result in 2021, he proved that all these 3 will be asymptotically infinitesimal free. Yeah, but you can observe, if you consider Jm by letter 1, then Jn will be Jn and the Wegener matrix. They are asymptotically infinitesimal free. Okay, so then we got something. If N and Bn are independent Wegeners, and you consider Jm, then the TAN and the Bm will be asymptotically monotone. Yeah, so it's not only GUE, they can be more general. Yeah, and in fact, since if you go back a little bit, by this form, so you can see the JMB, it can be many different ways. Can be choosing J per plus J per J, and you can add in more. But they will still be monotone independent, which means we're creating a way to construct lots of like a monotone independent monotone independent model, which later monotone independent. Sorry, random. Yeah, we're creating many models which are monotone independent. Okay, so yeah. So then here I will skip it. This is the definition of monotone independent. And thanks to Jose. So I skip the definition for monotone independent. Okay, so now we have a way to creating many monotone independent random matrix with respect to the partial trace. Okay, then now let's move on to say, if we have some monotone independent and we assume A and B are monotone independent, we consider P the polynomial of AB. How can we compute in the law over P? Which means how can we catch the Euler moment over P? Okay, and here we thanks to the work with Ottavio and Adrian. They have a really nice way to using matrix way to solve the cyclic monotone case, and we notice it's also a good tool to using for the monotone case. Yeah. So first, let's introduce a property. As long as you have a non-commutative property space, then you have two sub-algebra of C, where we assume AB are monotone independent. Then we have a such result. Okay. The trace of a phi of such a string, B naught A1, B1, and up to AN, BM, will be equivalent to the trace of the, they should have the phi, trace of phi. Okay. So you can see will be, so you consider computing these things. You just replace, it's equivalent, it's equal to you replace all the B by B prime. Where the B prime, you consider the phi entry-wise to each of the entries for the B. Okay. Yeah. So this property, and then now let me quickly, yeah. Then there's a thing I mentioned. Okay, it's a matrix way, which is connecting to solve the polynomial. Okay, so yeah. So when you consider these things, if you want to understanding, if you're given AB, where A and B are monotone independent, and you want to study this, which is the linear span of A and B. Okay. Oh, sorry, linear span of AB and BA. Okay. How can we study this law? And we're using this matrix tool. We know this one by this observation. This one is nothing but the trace of such a matrix, B0, AB1. Okay. So B0, AB1, if you consider B0, AB1 like this, then B0, AB1 will be nothing but the right-hand side. It's only one entries with the things we want. Then if you expanding that, then you got the trace phi of this string. And by the property we saw, this one is equal to, we consider the entry-wise, phi of entry-wise of each of the B term. Okay. So using this skill, it can help us to study this one easily. And actually, we can, okay, yeah, that's what I just mentioned. So then we can get exactly formula for the linear span of the AB and the BA. Then we have such formula. Yeah. Okay. And so wherever you have linear span, of course, it also cover the commutator and anti-commutator. So you can see, you just consider alpha beta is 1, and alpha beta is I minus I, then we have the corresponding formula. Yeah. Okay. Okay. So right now you can see we consider the linear span of ABBA, but whether we can say more, since right now it's only linear span or only commutator, anti-commutator. So let's move on to the more general polynomial. Okay. So now let's consider the following polynomial. When you're given two sub-algebra of C, and we assume the B is unitary, then we consider such polynomial P. By the sum of the Pj, Yj, Bj point, where Bj, Bj point is from B, but how about the Y? Okay, Y is come from this string. It's the AB, 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 those kind of a string. And we want to know whether we can really also computing those kind of law. Okay. So you can observe, since B we assume is unitary, so this one we can choose in 1, which means we consider the mix of the AB, sum of the mix of AB. Okay, and whether we can compute in this, yeah, then yes, and we have a precise formula. Okay, sorry, we didn't mention the P is as above, so P is this form. Then the formula will be goes like this. Okay, so what's the tilde? Tilde means Whenever you have a string A, B, A, B, A, B, then the Y tilde means you replace all the B by phi B. Okay. Then we have such formula. Okay. It's pretty abstract. Okay, and then I try to use an example to complete my talk. So let's consider following example. Now, if you're given a two independent Wegener matrix and you fix a knot, okay, then we consider following PM by this pattern. B to some power T, B to some power with T, B to some power T and B, and so on. Okay. So whether we can compute in a partial trace of this law. Okay. So first we observe the TN and the BN, they are asymptotically monotone. Okay. So since they are asymptotically monotone, we know let's underlie the non-commutative probability space and so on. We have two element AB, they are monotone independent with this result. Okay. So we convert the problem to computing this. Yeah. And as long as we have this, now we can apply this formula. So you can see the field of the PK, which means that pattern B, Y, B1 point plus B2, Y2, B2 point. Then we're just using our formula to get this slide. Yeah. Yeah. And then this computation looks very complicated. But there's a crucial thing is you can consider, I just replace define the alpha ki by this way. And this problem can be solved by solve this recurrent relation. Yeah, where all the C are Catalan number. Okay. So you can convert a problem to solve the recurrent relation of this equation. Okay. And turns out you got then we got precise formula of the PK, which is this pattern. Okay. And where you can see all the eta, zeta, theta, and all of them are represented by Catalan number. And we can go further, and we prove that this guy is between 0 and 1, and hence we got the P is nothing but Fowler distribution of this thing, where the omega is this. Okay. Yeah. So this method can be used into the many model that we can. Yeah, but depending on how difficult it is, this one takes some time. Yeah. Yeah. Okay, so that's it. Thank you very much.